So today's chapter is chapter 5, the Cauchy integral formula, the classical theorem of Green-Gauss. We shall review the classical theorem of Green and Gauss, the Cauchy integral theorem, the Cauchy formula, and we will see some analogies with the Gauss's integral theorems on electrostatics, and then will be followed up with some exercises. And so we begin by recalling the Green's theorem in the plane. First of all, we need to recall what is a path in the plane. What is a path in the plane? A path in the plane is a continuous piecewise smooth map gamma from AB to R2, right? What does he mean by piecewise, continuous piecewise smooth map? It should be continuous function, and then there should be a partition, right? Like for example, a circle is an example of a path. What is gamma of t? Gamma of t is cosine t comma sine t. But then what about the square? Square is also a path, but then when I parameterize the thing, the domain AB will be broken up into 4 pieces, right? On each of those 4 pieces, the thing is going to be differentiable, and at those partitioning points, the one-sided derivatives will exist, but they will not be equal, because when you go from here to there for the square, the derivative here will point this direction, derivative there will point in that direction. The right and left hand derivatives must exist, but they may not be equal. That's the thing. So that's a piecewise smooth. All the curves that we are going to be looking at, all the paths that we are going to be looking at will be piecewise smooth. So that's a blanket assumption that when I say path, I mean continuous piecewise smooth, alright. Then let us take 2 functions p of xy and q of xy on a certain domain omega. Let us say that p of xy and q of xy are defined on the whole plane just to begin with. Then or if it is not defined on the whole domain, it will be defined on some open set, and on that open set the image of the path lies. For example, suppose I take p of xy to be equal to 1 over x squared plus y squared. P of xy is 1 over x squared plus y squared. What is the domain? R2 minus origin. So I could take the path to be the circle cosine t comma sine t. That is, the image of the path should lie in the domain. Alright. So with this stipulation, the line integral p dx plus q dy over gamma, integral p dx plus q dy over gamma is by definition the Riemann integral, the usual Riemann integral a to b. You evaluate wherever there is x, you put the components of gamma, and wherever there is x, in place of x and y, you put the components of gamma. That is p of gamma t comma q of gamma t dot gamma prime t dt, right? So this p and q together is a vector field pi plus qj, or as a complex number p of xy plus I times q of xy, right, whatever it is. So or the pair p of xy comma q of xy. So you evaluate p of gamma t and q of gamma t, that is a vector, dot it with gamma prime t dt, correct? Alright, so if you write it out in full, it is simply, suppose gamma is gamma 1 t gamma 2 t. Suppose you say that gamma of t equals gamma 1 t comma gamma 2 t, right? Then it is simply p of gamma, wherever there is x you put gamma 1 t, wherever there is y you put gamma 2 t. When you see a dx, you put gamma 1 prime t dt, wherever there is a dy you put gamma 2 prime t dt. This is all review material. This is supposed to have been done in the first course. This is all a part of the Thomas and Finney's calculus and analytical geometry, right? All this material is there, and you have computed line integrals in your calculus. So just a review, just for fixing notations, right? Let's take the next one. Now, what is a path said to be a simple closed curve? Simple closed curve, first of all, it should be a closed curve. So gamma of A must be equal to gamma of B, And the second condition, it should not close up before, it should not close, this should not, it should only close up when A and B, at A and B, only the ends should join together, correct. Something like this should not happen. So, this means that given any 2 points in the middle, given any 2 points T1 and T2 in AB, such that T1 is less than T2, if gamma T1 equal to gamma T2, then necessarily T1 equal to A and T2 equal to B. The ends join up and only the ends join up and nothing else. So, this is not a simple closed curve, whereas this is a simple closed curve. So, is the concept of a simple closed curve clear? The ellipse is an example of a simple closed curve. What is the ellipse? A cos t, comma B sin t, that is a simple closed curve. The circle is a simple closed curve. The boundary of a square, when parameterized properly, is a simple closed curve, correct. So, this is a kind of thing that we are going to be working with very frequently. Now, what is the significance of simple closed curve? We have a very deep theorem called the Jordan curve theorem. Given a simple closed curve gamma in the plane, if I take the simple closed curve and remove the simple closed curve from the plane, that is the image is a set of points in the plane, right. So, you take a simple closed curve gamma and remove the image, right, then you are looking at the complement of the image. The complement of the image is union of two disjoint open sets, correct, two disjoint, union of two disjoint union of two connected open sets, right. It is the union of two connected open sets, the interior and the exterior. And only of these two connected components of these two open sets, one of them is bounded and the other one is unbounded. The bounded component will be called the interior, the unbounded component will be called the exterior. So, now we understand very clearly what we mean by saying that a point lies inside a circle. When I say when you are given a simple closed curve gamma and I say take a point P inside gamma or within the simple closed curve, the Jordan curve theorem tells you very clearly what that concept really means. The concept is very precisely defined. Okay. The Jordan curve theorem is a very deep theorem in topology. We are not going to be in any position to prove this, but then we are not here to prove all the theorems. We are going to be using theorems. These are all standard theorems, I mean, and we can surely use it because our goal, our task is in a different direction. Topology is not what we are studying in this course, we are studying analysis, complex analysis, right. Now, you are talking about a simple, so now what do we have? We have defined a path, we have defined a piecewise smooth, they are piecewise smooth curves. We are talking about line integrals along a path, and then we are interested in simple closed curves gamma, correct. So, in the Green's theorem all these things will come in, right. A line integral is present in the statement of the Green's theorem. So, I should tell you what is a line integral, I should tell you what is a path. A path is a piecewise smooth continuous function. And then we are talking about a simple closed curve, we are talking about inside and outside of a simple closed curve. What else appears in the statement of the Green's theorem? You remember the Green's theorem, right, from vector calculus? There is an important concept called orientation. There is a very important concept called orientation that is also a topological notion. See, there are two things involved in the Green's theorem. One of them is an analytical notion or the double integral. The other one is a topological notion of orientation. So, suppose if I am not going to be in any position to tell you in precise terms what orientation really means, it is going to be quite a difficult task to make this concept mathematically precise. It can be done, but that will be the subject of a different course perhaps, not the theme of this course. So, I am just going to intuitively explain to you what positive orientation really means. So, now let us take an omega to be an open domain in R2, which is bounded by finitely many piecewise simple closed curves. So, for example, a typical domain is depicted here, a big domain on which you have scooped out two small disks. You have taken a nice simple closed curve, right? It has an interior. Out of the interior, I have scooped out two disks, and this region in between is the region that I am looking at. This region is the region that I am looking at, right? This is the region. So, this is my region omega, and this region omega is bounded by how many curves? 3 simple closed curves, right? This region, so I am looking at a region omega in the plane, an open domain in the plane, whose boundary consists of finitely many piecewise smooth closed curves, C1, C2, etc. up to Ck. Suppose I take omega to be R2 minus the origin. Suppose I take omega to be R2 minus the origin. Does the boundary consist of finitely many piecewise closed piecewise smooth curves? No, correct, etc. So, we have this, it is a bounded, we will also be looking at bounded, let us take a bounded open domain, So, let us work with bounded open domains only. So, R2 minus the origin will be disqualified for two reasons. It is unbounded. Secondly, its boundary consists of a single point, the origin, correct? The origin is a boundary point. It is not inside the open set. And the single point boundary is not a simple closed curve. So, now we have the following situation. We have this kind of a picture. And what do you mean by saying that the boundary is positively oriented? Boundary consists of finitely many closed curves, and we have to orient these closed curves. What do you mean by positively orientation? Positive orientation. That means that each curve, each of these curves is a parameterized curve, right? It is described by a function gamma j from aj comma bj to R2, and the image is your Cj. Take the jth piece, take C2 for example. C2 will be described in terms of a function gamma 2 from an interval a2 b2 to R2, right. So, as the time t varies from a2 to b2, you will be tracing out the curve in some direction, either you will run clockwise or counterclockwise, right. It is a simple closed curve. So, you have to start at a point and you will return to that point as t runs from a2 to b2. You will either run clockwise or you will run counterclockwise, correct. Now, what is the positive? One of these will be considered as the positive orientation, the other one will be negative. So, now in other words, the problem boils down to putting a arrow on each of those curves, right. Look at the picture again, the arrow on C1 is going counterclockwise and the arrow on C2 and C3 are going clockwise, correct. These arrows are going, one of the arrows is going counterclockwise, the other arrows are going clockwise. How do I choose this? Why do I put the counterclockwise, why is C1 running counterclockwise and C2 and C3 running clockwise? This particular picture, the boundary has been positively oriented, correct. So, what do I have to now describe to you what positive orientation means, and the positive orientation can be described in the following terms. You imagine the region omega to be a lake, right. You have a nice C1, right, and there are a nice simple closed curve, and the simple closed curve encloses a region, correct, bounded region. Think of the bounded region as a lake, and think of the C1 as a road going around the lake, and the C2 and C3, they are also simple closed curves, correct. Think of them as islands. No, sometimes you have these lake, a huge lake, and in between the lake, inside the lake there are small islands, right? For example, in Udaipur, the Fateh Sagar Lake is an example. It's a nice lake, but inside the lake there is a small islet or an islet, a little tiny island in the lake. So there are two islands in the lake, correct? So they also have their boundaries, correct? So I could drive along the outer, so this particular lake has three pieces of boundary. The big one, C1, and there's a C2 and there's a C3. The boundary of the boundary of those little islands inside, and the big boundary inside which the entire lake is sitting, correct? Now think of this as, think that you are driving along the boundary. You are having a nice time and you are driving along the boundary as you are going to have tomorrow for your break. You are going to be driving along the lake, and when you drive along the lake should always appear to your left. The driver should see the lake on his left. That direction is the positive direction. So let us go back to the picture and see whether it has been correctly done. So you have the lake here, correct? And you are driving along the outer boundary. Is the lake appearing on the left? It is. What about inside? It's again appearing on the left. So that is the way to orient the boundary. So if you do it that way, then you would say that it has been positively oriented. So is the concept of positive orientation clear to everybody? All right. That's all that I'm going to say now. I'm not going to try to define it precisely or whatever. So that's what, let me just write this down as a slide. Figuratively, imagine omega to be a lake and C1, C2, C3 as roads bounding the lake. As we drive along Cj, the lake must appear to the left. That's the meaning of positively oriented. Now for a simple closed curve enclosing a region, suppose I take a simple closed curve enclosing a region. Let's look at this example. So now there are no islands inside. It's just a simple lake. All right. So now what is the correct way to what is the positive orientation? The counterclockwise. So it is simply the counterclockwise. So if it is a simple closed curve without any islands inside, then it is the boundary is simply going counterclockwise. Correct. If there are islands inside, then those islands you will have to those boundaries will go. So that's about it as far as boundary orientation is concerned. So now we shall always assume that we have a bounded open region whose boundary consists of finitely many oriented simple closed curves, okay? And I'm going to take the positive orientation unless mentioned otherwise. If I say oriented, it means positively oriented unless the contrary is explicitly mentioned. All right. So now let us take, I'm going to call omega bar to be this omega together with the boundary. You have the interior, in this picture you have the interior omega, and then along with this interior you throw in the boundary also. In the previous picture you take, this is your omega, the blue lake, and throw it and take the union of this lake along with those boundaries, okay. So then when I do that, I am going to call it omega bar, alright. I am going to call it omega bar. Omega bar is omega union C1 union C2 union C3 union Ck. That is the closed region together with its boundary. So and you are given two functions pxy and qxy which are continuously differentiable on the, not only is it continuously differentiable inside omega, it should also be continuously differentiable on the boundary. What do you mean by saying that it is continuously differentiable on the boundary? What do you mean by saying that it is differentiable here? Continuously differentiable here. That means that there must be a certain disk around this point in which they are both continuously differentiable, correct. It should be differentiable, it should be continuously differentiable in the interior. Interior is an open set, so there is no problem. On the boundary, what is the meaning of saying something is continuously differentiable? Take the boundary point, then I should be then there is a small disk, and in that disk P and Q are defined, the partial derivatives exist and the partial derivatives are continuous, and this should happen at each and every boundary point. Then I will say that Pxy and Qxy are two continuously differentiable functions on an open set containing the omega union C1 union C2 union Ck, correct. So, there is a little more room, not just it is not like outside C nothing exists. There is a open set containing omega bar. In that open set the functions Px and Qx are partial derivatives exist, are defined first of all, the partial derivatives exist and the partial derivatives are continuous. Is this clear? What do I mean by saying that Px and Qx are continuously differentiable on omega bar? I will simply say that Px and Qx are continuously differentiable on omega bar. By definition, it means that it is defined on an open set containing omega bar and continuously differentiable that. Differentiability is defined on open sets only, but then now, so when I have a set which is not open, I have to modify it suitably, and the obvious modification is that there should be an open set containing the thing on which it is continuously differentiable. The Green's formula is finally up on the slide for you. What do the Green's formulas say? If you are first of all given an omega, you are first of all given a bounded region omega, right, which is whose boundary consists of finitely many simple closed curves, correct, and these simple closed curves have been positively oriented. The arrows are showing positive orientation. When you drive along them, the lake always appears to the left, and then you are given these two functions Pxy and Qxy, which have continuous first order partial derivatives on omega bar, or rather in a open set containing omega bar, correct. Then integral P dx plus Q dy over the boundary equal to the double integral del q by del x minus del p by del y dx dy over where what is the meaning of integral of C of P dx plus Q dy? C is the union of C1 union C2 union Ck, and so this integral, by this integral I mean integral of C, I mean integral of C1 plus integral of C2 plus etc plus integral of Ck, correct. This is the meaning. Everywhere the integrand is always P dx plus Q dy, and this little circle on the integral signifies that we are integrating over a closed curve. That is all that means, nothing, it does not mean anything else, alright. Is it clear? The Green's formula, this is the Green's formula. Is this what you are done? Is this what you are familiar with? Now, let us now come back to complex analysis, and you are taking again the usual decorations are there on the screen. You have omega bar, you have omega and its boundary components C1, C2, Ck, and then you have a function fz which is analytic in an open set containing omega. What do you mean by saying that fz is analytic in an open set containing omega? F equal to u plus iv, where u is the real part of f and v is the imaginary part of f. U and v are functions of x and y, correct. And so these functions u and v have continuous first order partial derivatives on omega bar, meaning in an open set containing omega bar, correct. And u and v must satisfy the Cauchy Riemann equations, then you will say that the function is analytic. That is the meaning of the phrase f is analytic, correct. So, you take such an analytic function, then I want to talk about integral fz dz. What do you mean by integral fz dz? Here is a definition. It means integral u dx minus v dy over omega plus I times integral u dy plus v dx. This is a definition of integral fz dz over omega. Where does this business come from? Intuitively, see what is f? F is u plus iv. You are looking at, so what is fz dz? Fz dz is u plus iv into dz. What is dz? Dz is dx plus I dy. So it is u plus iv into dx plus I dy, and when you write it out, you are going to get u dx minus v dy plus I times u dy plus v dx. So when you integrate this, it should be integral of the real part plus I times the integral of the imaginary part. So is this okay? Is it clear what integral fz dz really means? It is consists of two line integrals, and you have to take the first one plus I times the second one. That is the meaning of integral fz dz, the definition of integral fz dz. That is it, finished. Alright. So now let us try to see what is the significance of analyticity in this context. So now let us apply the Green's formula. Let us apply the Green's formula. Integral fz dz over c is going to be integral of u dx minus v dy over c plus I times integral of u dy plus v dx over c, correct. Now let us apply the Green's theorem to each of these pieces. Remember, boundary is oriented positively, that is a blanket assumption. Then you apply the Green's theorem, p dx plus q dy integral will be equal to a double integral del q by del x minus del p by del y. So what is your q? Q is v. So del q by del x minus del p by del y dx dy plus I times double integral, yeah, del q by del x minus del p by del y, correct. What does the Cauchy-Riemann equation say? U sub x equal to v sub y and u sub y equal to minus v sub x. So each of these is 0. Each of these is 0. So integral fz dz over c is 0. What is the meaning of saying integral of fz dz over c is 0? Does it mean that integral fz dz over each of the cj's is 0? No. Does this mean, what is the, so what do we get now? So what do we get? We are saying integral fz dz over c equal to 0. Integral fz dz over c is 0. What is the meaning of the statement? It means integral fz dz over c1 plus integral fz dz over c2 plus etc. plus integral fz dz over ck is 0. I am not saying, mind you, I am not saying that each of the integrals individually are 0. It is false to say that integral fz dz over c1 is 0, integral of fz dz over c2 is 0. That statement is false. The sum of the integrals is 0. That is the correct statement. Alright? Okay. Is it clear? This is the Cauchy's integral theorem. In particular, if fz is analytic within and on a simple closed curve, I spelled out what do you mean. A function f is said to be analytic or differentiable on the curve C means it is analytic or respectively differentiable in a neighborhood of each of its points. So you take a point on the boundary, in a neighborhood of this point, the function should be defined and analytic. So this should happen for each of the boundary points. That's the meaning of saying that the function is analytic on the curve. So in particular, if fz is analytic within and on a simple closed curve C, then integral fz dz over C is 0. This is a special case because there is only one boundary piece. It is a simple closed curve, the boundary has only one piece. But then if you take a lake with islands in them, then the boundary will consist of several pieces and you integrate over each of these pieces and sum them and you are going to get 0. of course the boundary has to be positively oriented. Now I think I would like to say a few words about analyticity and complex differentiability. This has been, I have postponed saying this, I could have said this at any time, but then now I think is the appropriate time to say it. So for many books, I am sure I have not looked very carefully at Kreyszig lately, but many books, analytic simply means complex differentiable. Complex, for most books, complex differentiable and analytic mean one and the same thing. So for many books, a function fz is analytic means u sub x, u sub y, v sub x, v sub y, or its complex differentiable at each of its points. Many books, for many books, function fz is said to be analytic if limit as h tends to 0, f of z plus h minus fz upon h exists for each of the points. It's complex differentiable at each point of the domain. That's the meaning of complex, that's the meaning of analytic for most books. Whereas what is our definition of analyticity? For us, analytic means that it should be complex differentiable and the derivative should be continuous. That means not only do I want u sub x, u sub y, v sub x, v sub y to exist and satisfy the Cauchy-Riemann equation, these 4 first order partials must be continuous. So it may appear to you that our definition is more stringent, it's more strict than the usual definitions. It turns out that that is not the case. One can prove a theorem, and that theorem is called the Gursat Lemma, saying that if f is complex differentiable, then f prime z is continuous. That's a theorem. And so ultimately, the two concepts turn out to be one and the same, and we are not going to be interested in developing complex analysis in this generality. We won't be proving the Gursat Lemma, so we will be assuming at the outset that analyticity means complex differentiable plus f prime is continuous. That can be taken as a definition because that is anyway a consequence of Gursat Lemma. So there is no harm in making that, putting that into a definition right at the beginning. Now why is it that we have done this? Why is it that we have not followed the tradition of most people? Not all. This is not my definition, by the way. There are a certain number of books which take the definition of analyticity should to be that f is complex differentiable plus f prime is continuous. Our definition is also followed by certain authors, but a large majority of the authors don't follow this convention. All right. For majority of the authors, analyticity means complex differentiability, but for us it is complex differentiability plus the continuity of f prime. Now this is we are in the minority. There are a certain number of books which do follow our definition, but we are in a minority. But for engineering students, for teaching engineering students, I think this is slightly better. Our convention is slightly better because really there is no difference thanks to the Gursat Lemma. Ultimately everything turns out to be nice, but the Gursat Lemma is a very interesting and very important theorem, but it has mathematical significance. For an engineer it has no significance. Okay. So to have a nice and elegant mathematical theory, maybe one should say that analytic means complex differentiable and then prove the Gursat Lemma, but we don't have time to do that. It's not difficult to prove the Gursat Lemma, by the way. It will take some time. So the development will take a little longer and we don't have that extra time, so we are taking the short route. We are doing this because we have used the Green's theorem to prove the Cauchy integral theorem. Integral fz dz over c equal to 0. Where did this come from? This came from the application of Green's theorem. And when you want to apply Green's theorem, you need the continuity of the first partial derivatives. When you want to apply Green's theorem, you need the continuity of the first partial derivatives. If you don't have the continuity of the first partial derivatives, you cannot apply Green's theorem, and so the proof of integral fz dz over c is 0 will have to be different. It will have to avoid Green's theorem, it will be longer. The proof of the Cauchy integral theorem will be much longer if you do not assume the continuity of f prime z. And once again, from the point of view of engineering, for teaching engineering students, it is not worthwhile giving the longer proof and dropping the assumption of continuity of f prime z and trying to avoid Green's theorem. Right. So, that is the reason why our definition of analyticity differs from most standard definitions. All right. But this is not original or anything. Let me repeat, there is a small number of books which use this definition of analyticity and which rely on Green's theorem. So, this was a few important words I wanted to say about the definition of analyticity. Now, let us get to examples. Let us look at number of examples. They are easy examples, so I will go very fast. So, this curve is cos t comma sin t, circle traced counterclockwise or clockwise when t runs from 0 to 2 pi. How is the circle traced? Counterclockwise. So, it is positively oriented automatically. Let us calculate integral z to the power n dz over c. Of course, if n equal to 0, 1, 2, 3, directly the answer is 0 by Cauchy's theorem. But then if n is minus 1, minus 2, minus 3, etc., I cannot apply Cauchy's theorem because 1 over z squared, 1 over z cube, etc., are not analytic inside the circle because origin lies inside the circle. So, we have to directly calculate it by parameterization. What is along the along the curve C, what is x? X is cosine t and y is sin t. So, z is what? Cosine t plus I sin t, z to the power n is cosine t plus I sin t raised to the power n, and then dz is d of cos t plus I times sin t. So, what is the first one? It is cos nt plus I times sin nt into d of cos t is minus sin t dt, d of sin t is cos t dt. Therefore, we get all in all, pull out the I and we get cos nt plus I times sin nt into cos t plus I times sin t 0 to 2 pi cos n plus 1 t plus I times sin n plus 1 t dt, which is 0 if n equal to minus 1, 2 pi I if n equal to minus 1. If 0 if n is not equal to minus 1 and 2 pi I if n equal to minus 1. So, what is our conclusion? Integral c z to the power n dz equal to 0 if n is not equal to minus 1, integral dz upon z over c equal to 2 pi. In particular, integral of 1 over z squared dz is 0, integral of 1 over z cube dz equal to 0 over the circle, right? Clear? Simple example. We will look at more examples as we go along. So, now let us get to the next business, the Cauchy formula. The Cauchy formula says that if f is analytic within and on a simple closed curve C. So, you are given a simple closed curve C and f is analytic within and on the simple closed curve, then integral fz dz over C upon z minus a equal to 2 pi I times f of a. Integral over C fz dz upon z minus a is 2 pi I times f of a. Is it clear? And as usual, C is traced counterclockwise. Please write down just the formula and nothing else. If f is analytic within and on a simple closed curve C, then integral over C fz dz upon z minus a is 2 pi I into f of a. 2 pi I times the value of the function at the point A. Denominator is the integrand is troublesome at which point? At the point z equal to a, correct? All right. So, let us look at the proof of the theorem. Proof of the theorem. First of all, choose a small circle with center at A, correct? And look at the region in between. So now I have scooped out a small circle and I am going to make it an island in the middle. And let us apply the Cauchy formula for this region omega that lies in between the two things. It is going to be 0, right? Because in between the two things the function is analytic and on the boundary also it is analytic. The only troublesome point is the center of the circle, which is A, and so there is no problem. So integral over C fz dz upon z minus A plus integral over gamma fz dz upon z minus A would be 0 if gamma were oriented positively, but here the picture, the gamma is oriented negatively, and hence you see the negative sign here, correct. In the Cauchy formula I would have had a plus sign here if I had put the arrow on the gamma on the green circle were going in the other direction. If the green circle were traced clockwise, then I would be putting a plus sign here, but the green circle is being traced counterclockwise, so I am putting a minus sign because I am going to push it to the right hand side eventually. That is the point. That is the reason why I am doing this funny thing. Alright. So let us push the thing on the right hand side, both of them traced counterclockwise. Nice. Integral of fz dz upon z minus A equal to integral fz dz upon z minus A over gamma epsilon. Now let us do this gamma epsilon, let us modify this gamma epsilon integral slightly by adding and subtracting a f of A. F of A is a constant, so it comes out of the integral and I am left with dz upon z minus A. We have calculated integral dz upon z when the circle had center at the origin. Now the circle has center at A, and instead of dz upon z we have dz upon z minus A. So what will be the value of the integral? Again it will be 2 pi I, correct. Exercise, parameterize and calculate this integral directly and obtain 2 pi I for this integral. So this piece will be 2 pi I times f of A, correct. I am leaving it this checking for you to do. So we have now integral fz dz over C, integral fz dz upon z minus A over C equal to 2 pi I times f of A plus integral gamma epsilon fz minus f of A upon z minus A dz. So far we have come. Now what are we supposed to show? We are supposed to show that this equals this. In other words, we are supposed to show that this business out here is 0, correct. Now this term and this term do not depend upon epsilon. This is the only term that depends upon epsilon, and epsilon was an arbitrarily small positive radius. So I can allow the epsilon to go to 0 in this equation. This will remain constant, this will remain constant, and I will show that the limit of this as epsilon goes to 0 is 0, correct. That is the whole trick. Alright. Now to do this effectively, let us parameterize the circle centered at A. How do you parameterize the circle centered at A? It will be A plus epsilon cos t plus I epsilon sin t, right. It will be A1 plus epsilon cos t comma A2 plus epsilon sin t, where A is A1 comma A2, correct. So the parameterization is Z equal to A plus epsilon e to the power it. So what is dz? Dz is epsilon I e to the power at, right. Dz will be epsilon I e to the power at. What about z minus a? Z minus a is epsilon e to the power it. So the epsilons will cancel out and the e to the power it will also cancel out, and I will be left over. Is that yes or no? Yes. So now what are we left with? Integral 0 to 2 pi. Where does t go from? T runs from 0 to 2 pi, running counterclockwise, right. So it's integral 0 to 2 pi f of what is z? Z is a plus epsilon e to the power I t minus f of a. Now, what happens to this as epsilon goes to 0? Function is continuous. The function f is differentiable and so it is continuous. So, what happens to the integrand as epsilon goes to 0? It goes to 0. So, that is the reason. So, ultimately you are left with integral fz dz upon z minus a will be 2 pi I times f of a. Is it clear? Proof of the Cauchy integral formula is one of the, this formula lies at the heart of complex analysis. This is the central formula. We have derived the most important formula in complex analysis. This is the one. This is a very important formula. It lies at the heart of complex analysis. Is it clear? Right? Yeah, okay. Sorry. A lies in interior of C. Thank you very much. The correction is A should lie in the interior of C. In the picture, we tacitly assumed that, but if A lies outside, then straight away by Cauchy integral theorem, the thing will be 0. That is absolutely good observation, very good observation. A should lie in the interior of C, that should have been mentioned, and now it is here. All right. So, it is very, very important that the curve C is traced counterclockwise, that is also important, and A should be inside. If A is outside, the answer will be 0. Correct? Yeah. So, please make this correction that integral fz dz upon z minus a over C equal to 2 pi I into f of a, provided A is in the interior of C. Very important. Once again, A should lie in the interior of C. Very important point which was raised by somebody. Absolutely good. Absolutely wonderful. Good point. Very good point. There is a very important hypothesis I missed out in the stating the Cauchy's theorem. All right. Now, if you look at the Cauchy's formula, if you stare at the Cauchy's formula, it should, it's one of the, it's a very remarkable formula in some sense. And I don't know whether you have studied these things. Have you studied the Gauss's divergence theorem in electrostatics? What does the Gauss's theorem in electrostatics say? It says that the total electric flux over a closed surface equals the sum of the charges inside. Is that correct? The Gauss's theorem in electrostatics says that the total electric flux over a closed surface equals the sum of the charges inside the surface. It depends upon the units that you use. I am talking about the CGS units. If you use MKS units, there will be an epsilon 1 over 4 pi epsilon 0 floating around. There will be a 1 over 4 pi epsilon 0 floating around if you use MKS units. If you use CGS units, that 1 over 4 pi epsilon 0 will not be there. So, depending upon the units chosen, there will be a constant, but let us assume that the units are chosen so that the constant is 1. So, once again, the Gauss's theorem in electrostatics states that the total electric flux over a closed surface equals the sum of the charges lying inside the surface. I am assuming that there are only point charges. How does one prove this very important theorem in electrostatics? How does one prove this very important theorem in electrostatics? This is one of the applications that you will give to your students, right, when you do the divergence theorem. When you do the divergence theorem in vector calculus, this is one of the most important applications you will give. How does one prove it? Do you remember? No? Okay. So, what is the, look at the picture, look at this is the surface sigma, and that is the outer normal vector. I have drawn the outer normal vector and the electric field vector is described. What is the flux of the electric field over the closed surface? It is E dot n d sigma. What is this d sigma? It is the area element, correct? In vector calculus, you have the area element, it is a area element, and this is a total electric flux equals the sum of the charges lying inside. What do you do? How do you prove the theorem? The theorem you will prove by saying, God, the numbering is completely gone, but never mind. So now you have these charges which are lying inside. You scoop out spheres inside, correct? You scoop out spheres inside, right? And then you look at the, you look at what? The region inside, right? You look at the region in between the spheres and you apply the divergence theorem. Look at what we have done here. You're taking the charges which are finitely many and you're scooping out spheres centered at these charges. You remove the balls, closed balls which center at these charges and look at the region in between sigma and these spheres. The green, the region depicted in green, right? This region. And what are we going to do to that region? It's a charge-free region, right? It's a charge-free region, and in a charge-free region, divergence is 0. What is the divergence? When I tell you divergence, if the divergence is non-zero, it means there are sources present. But we are looking at a charge-free zone. You have removed those spheres and you are looking at the region in between. In between there are no charges, right? All the charges are inside the spheres and those spheres have been removed. Those balls have been removed. And so in between the remaining portion there are no charges. And if there are no charges, then the divergence is 0. And if the divergence is 0, you apply the Gauss divergence theorem. What is the Gauss divergence theorem from vector calculus? Could you please recall the Gauss divergence theorem from vector calculus? It says that integral E dot n ds over the boundary of omega equal to triple integral divergence of E dx dy dz. The triple integral is 0 because there are no charges. And what is left over? Integral E dot n d sigma over the boundary of omega. What is the boundary of omega consists of? The original thing, right? The boundary of sigma consists of what? Where is the picture? Let me just, here is the picture. The boundary consists of this thing and the normal will point outward, and for these things the normal will point inside, exactly as we did for the lake. The outermost curve was going counterclockwise, the inner ones are all going clockwise. The outermost ones, the normal is facing outside, the inner ones, the normal is facing inside. Same kind of convention. And so the integral over this plus integral over these things is 0. Now let the epsilon, now let us assume that the radius of these balls are epsilon and let epsilon goes to 0 and you calculate the contribution from each one of these things and you are exactly going to get q1 plus q2 plus q3 etc. That is exactly what. So the proof of the Cauchy integral theorem that we have given is exact analog of the corresponding theorem in electrostatics. It is exact analog. In fact, you can think of the Cauchy integral formula as a two-dimensional version of the Gauss's divergence theorem, and the proof is also very similar. Instead of the Cauchy-Riemann equations, you are having here the zero divergence in charge-free regions. You understand the analogy between this and the Koshy theorem and the Gauss's theorem? Clear? All right. This is something that you can tell your students. All right. Let us look at the example. Example 2. Let us try to evaluate integral 0 to 2 pi x of e to the power I t. Let us evaluate integral 0 to 2 pi x of e to the power I t. So, once again, here we are going in the opposite direction. The thing is given to you in parameterized form and we are trying to find the curve. So, you see the 0 to 2 pi should suggest to you that we should take c to be e to the power I t and t should run from 0 to 2 pi. Take the circle traced counterclockwise. When you take a circle traced counterclockwise, what is dz? Dz is I e to the power I t dt, or dt is dz upon Iz. So, we are going in the opposite direction. In the first example, we went in the other direction. The circle was given to you and we wrote dz in terms of dt, but now we are writing dt in terms of dz, right. So, now let us write the integral 0 to 2 pi x of e to the power I t dt as integral over c, integral over c x z dz upon Iz, the I comes out, and then you simply apply the Cauchy formula, no? What is your function now? I comes out. So, x z upon z, you are given a circle, exponential function is analytic everywhere, and so you are looking at fz dz upon z minus a. What is your a? 0. What is your fz? E to the power z, that is it. So, it is 2 pi I times f of a, which is exactly this, and the I and I cancels out and you get 2 pi. Next example, compute sin z upon z dz. Compute sin z upon z dz, where c is the ellipse alpha cos t plus beta sin ti. Alpha cos t plus beta sin ti, t runs from 0 to 2 pi. Once again, we have f of z equal to sin z, a equal to 0. What? Remember the Cauchy formula, fz dz upon z minus a integral over c is 2 pi I times f of a. A lies in the interior of c. A lies in the interior of c, and sure enough, in our example, the a does lie in the interior of c. And what is the function that you are taking? Sin z, which is analytic everywhere. So, it is 2 pi I times sin 0, and the answer is 0. Good. Is it clear? Routine. One more example. Let us calculate integral over c e to the power z squared upon z cube dz, where c is the ellipse a cos t plus b sin t. We cannot use Cauchy formula directly. Do we have fz dz upon z minus a? No, we have z cube. We have now z cube. So, we have to do a little tinkering with this. So, we add and subtract a 1. So, e to the power z squared minus 1 upon z cube dz plus dz upon z cube. Now, what is dz upon z cube over c? 0, but then we do not have a circle, we have an ellipse. It is 0, that is correct. Integral dz upon z cube over c is 0. Answer is correct, but c is not a circle, c is an ellipse. Anyway, now what is the function that you are going to be taking for the first one? Fz is going to be e to the power z squared minus 1 upon z squared. Then it is fz upon z, and so now we have to do two things. We have to show that e to the power z squared minus 1 upon z squared is analytic everywhere, and let us define f of 0 to be the limit of this. What will be this? No, 0? Use L'Hopital's rule. Or write the power series for e to the power z squared. 1 plus z squared plus etc. Right? Z to the power 4 upon 2 factorial plus etc. The 1 and the 1 cancels out. You are left with z squared. So, what shall we define f of 0 to be? 1. That's right. So, let us take this definition. And now, you have to check that this function is analytic. You have to check that this function is analytic, but then you believe that then your f, then I can apply the Cauchy formula for the first piece, and for the second piece you have to convince me that the answer is 0 regardless of the fact that C is an ellipse. We are not looking at a circle, we are looking at an ellipse. Nevertheless, the answer is going to be 0. That's an exercise for you, and that's coming up. So now integral C e to the power z squared dz upon z cube is integral fz dz upon z plus integral dz upon z cube. Now your number of exercises for you. First of all, you have to show that the f is analytic on C. The second problem is prove that integral of dz upon z cube equal to integral of dz upon z cube over C1, where C1 is a circle, epsilon e to the power it. That this integral is the same as this integral. You have to use a Cauchy's theorem. That whatever fz we have defined, no? That fz. E to the power z squared minus 1 upon z squared. That is analytic with f of 0 to be 1. Correct? You have to do that. And the second thing you have to do is that integral over the ellipse is the same as the integral over a circle. If I take a small circle epsilon of radius epsilon, the usual thing that you have to scoop out the circle and apply the Cauchy's theorem to the region in between the ellipse and the circle. Third is to finish the calculation. The third exercise is to finish the calculation. All right? So please do this exercise. And the next exercise is, let E be the ellipse. Let E be the ellipse a cos t plus b sin t. T running from 0 to 2 pi. By evaluating dz upon z directly as well as using the Cauchy formula, by evaluating this integral dz upon z in two different ways. First is you use Cauchy formula and calculate it. Second is to directly parameterize and do the evaluation and compare the results. Find the value of this. By writing two different expressions for the integral, find the value of integral 0 to 2 pi dt upon a squared cos squared t plus b squared sin squared t. This exercise is available in several places. One of them, one of these sources is Polya and Latta's book on complex variables. It is also there in Needham's book on visual complex analysis. The other place to find this would Needham, visual complex analysis. Very popular book. I mean, Polya Latta is a very old book. I mean, it's been a Needham, Dham, Needham, visual complex analysis by Needham. Lots of pictures you will find in that book. Then the next question is, by computing integral over the unit circle of z plus 1 over z to the power n dz upon z in two different ways, evaluate integral 0 to 2 pi cos to the power 2n t dt. Can you compute integral 0 to 2 pi sin to the power 2n t dt along similar lines? Right. So I am asking you to calculate integral 0 to 2 pi cos to the power 2n t dt and sin to the power 2n t dt using Cauchy formula. The next question is, calculate integral dz upon z cube minus 1 mod z equal to 6. Calculate integral dz upon z cube minus 1 mod z equal to 6. The next question is, compute the integral 0 to 2 pi x of e to the power I theta plus minus I theta d theta. Eighth question, given that integral minus root 3 to plus root 3 dx upon x squared plus 1 is 2 pi by 3, calculate integral over gamma dz upon z squared plus 1 in the following cases. When gamma is a semicircle joining minus root 3 and root 3 in the upper half plane, gamma is a semicircle joining minus 3 and root 3 in the lower half plane, and gamma is a circle of radius root 3 centered at the origin. Given that minus root 3 to root 3 integral dx upon x squared plus 1 is 2 pi by 3. Calculate integral dz upon z squared plus 1 over gamma, when gamma is a semicircle or arc joining minus root 3 and root 3 in the upper half plane. Gamma is a semicircular arc joining the lower joining minus 3 and minus root 3 and root 3 in the lower half plane. Gamma is a circle of radius root 3 centered at the origin. Show that if Pz equals z minus a to the power k times qz, where q of a is not 0, then p prime z upon pz is k by z minus a plus q prime z upon qz. It's a very trivial exercise. Ninth one, the first part is a completely trivial exercise, and show that if Pz is a polynomial, 1 over 2 pi I times integral p prime zeta upon p of zeta d zeta equals the number of roots lying inside the circle mod z equal to r. And then integral z to the power j p prime z upon pz dz 1 over 2 pi I mod z equal to r is a sum of the jth powers of the roots lying inside mod z equal to z to the power j. Sum of the jth powers of the roots lying inside mod z equal to r. It's a very important problem, it is very useful. Suppose you know that there is only one root inside the circle, then you can capture that root as an integral. That's the significance of this question. Suppose you know that there is only one root in the circle, then by writing down this integral and taking j equal to 1 here, then that root comes out as an integral over a circle. See, if I give you a polynomial, you are not going to be able to give me a formula for the root, right? But you know that the root lies inside the circle, and you know that there is only one circle, you know there is only one root inside the circle. So I take that particular circle and integrate this expression z p prime z upon pz, then what will it be? It will be the value of the root. So the value of the root can be expressed as an integral over a circle. You can use these ideas to prove many theorems. So here I shall stop. So with this I shall conclude this particular chapter, chapter 5, and we shall take up the solutions of these exercises pretty soon.